Alright, now it's time for the fun part. I'm going to show you everything I've taught you in the last few videos with Numpy, actual software. So this will be great. Alright, so right now I'm using a Jupyter notebook, and if you don't have a Jupyter notebook, I highly recommend you to install it. It's really good for doing Python stuff. But anyways, so you want to import NumPy as MP at the beginning. So let's just go ahead and do that. Now, defining vectors is fairly simple. All you need to do is u equals mp.array 2, 1, 1. That's it. When you do that, you have the vectors u and v. And to take a dot product of vectors, you just do np dot u and v, and then you get the dot product. Now, you define matrices in a similar way, actually. You just do rather a vector vectors approach. So to define a matrix A, it would just be, for example, it would be np.array. The vectors 1, 2, 3, 2, 4, 7, and 3, 7, 9. Now notice that uh, 1, 2, 3, 2, 4, 7, and 3, 7, 9, they will each be row vectors of the matrix, not column vectors. So let's go ahead and run that. And the matrix vector product is actually use the same syntax. It's just np.dot as well, ironically. Um, uh, Personally, I don't like the name dot because you get that and dot products mixed up. I prefer the term general multiply, but whatever, it is what it is. So let's go ahead and run this. So that means, so the output is just the vector that results from a times u. And for matrix product, you just do np dot dot 8a, aa, where a is the matrices. So let's go ahead and do that. Perfect. So that's the result of a times a, or the matrix a squared. And determinant is also really easy. You just call np.lineage.determinant of a and get a determinant. Now NumPy is now sometimes NumPy does weird stuff like this, but that's because of a numerical precision error. So it's really -1. It's not going to be negative 0.999997. And inverting a matrix is also fairly similar. Since the determinant is non-zero, we know that the matrix will have an inverse, so will be legal. So let's go ahead and try to find the inverse of A. Alright, so this is an inverse of A, and notice how we have some weird terms that are 10 to the negative 16. Um, that Those are really zero. It's not, no, it's really zero. And we can confirm that A inverse times A is I. So let's go ahead and do that by doing np dot dot A inverse A. Perfect. So you get 1, 1, 1, and then those are zeros. And these, they are zeros. Okay. 10 to the negative 15, it's 0. All right. Don't worry about it. And the identity matrix, you just do np.I whenever you want to call one, where we put in number 3, this will be a 3 by 3 identity, and so on. And finding eigenvectors and eigenvalues is also very easy. You don't have to, solve the characteristic equation or anything. All you have to do is go to NumPy and type np.lineage.eig, and you get the eigenvectors and eigenvalues. So let's run that. So that means the eigenvalues of this matrix are this negative 14.869, 0.07145, and negative 0.94. And the eigenvectors are the columns of this matrix. So it'll be this. So this will be the eigenvector corresponding to this first eigenvalue. This will be the second eigenvector corresponding to the second eigenvalue, and so on. Now, D is currently in vector form, and we want to turn it into a diagonal matrix form. So we do D equals np.diag D. So when we do A equals PDP inverse, we will show that the result of that is A, 1, 2, 3, 2, 4, 7, 3, 7, 9. And if we go back here, we can see that this is A. So now how for the fun part, tensors. Remember in the first video I talked about how tensors are just multidimensional arrays. Well, this is exactly the case. So you literally put in a 4D array, and here I did np.random.rand. So basically form a 7 by 7 by 7 by 7 array, each of random values from 0 to 1. and then I just define a matrix, 2D tensor, um, where this is basically a matrix. Now, remember from my Einstein video that tens you can define tensor operations using something called Einstein summation notation, and so let's define. So let's say you want to do an operation where you take the sum over the last two indices of the 4-index tensor, as well as every index of the matrix, and that will give you the PQ index of the resulting array. So you just do PQRS RS becomes PQ. This is basically the equation JPQ equals ERI PQRS times DRS, sum over RR, sum over RS, if you remember from that video. And J is defined in a different way, and you'll later see my Hartree-Fock video that this is actually based on Hartree-Fock, and this is not just randomly made up. Well, actually the ER and D are randomly made up, but you know, the things we do in the Hartree-Fock video will be very similar to this. So let's go ahead and define our tensors, and let's go ahead and run this as well. And then we get J and K, which are matrices that result from tensor products. So I bet you never learned that in linear algebra, but this is pretty cool, and you need to know this for computational chemistry. And everything I did here, this is analogous to the actual quantum chemistry. ERI here represents an electron repulsion integral, and D is the density matrix, J is the Coulomb matrix, and K is the exchange matrix. Now, obviously, they aren't real values and don't have any physical meaning, but I'm just showing you to give you a preview. Now, now I'm giving you a challenge problem. You ready? Your challenge is to use Einstein to do a matrix-matrix product using the rules you learned about Einstein, using np.einstein. Go ahead and pause this video right now, and I'll give you the solution in a little bit. All right, so let's do the Einstein challenge. So remember from the definition of a matrix multiplication, you have Cij equals Aik times Bkj sum over K, right? So that means the operation will just be np.ein sum Ik Kj becomes Ij. And for this one, we'll just use the matrix A again to compare our answers to the A times A. So let's just go ahead and do it, and let's run it. And as you can see, we get the same answer as above. If you don't believe me, we can you can do np.a, and here you have it: 14, 31, 44, 31, 69, 97, 44, 97, 139. Well, I hope you enjoyed this walkthrough of Numpy. We will definitely be using Numpy and Jupyter Notebooks for our future quantum chemistry coding tutorials. So get used to it now. Well, have a great day, everyone.